Let's investigate this research question. Are some drivers more likely to stop at a stop sign than others? Researchers observed cars approaching an intersection with a stop sign. And for each car, they observed whether it came to a complete stop or not, and whether it was a single vehicle approaching the intersection alone, whether it was a lead vehicle approaching the intersection with another car behind it, or a following vehicle approaching the intersection with a different car ahead of it. So here, we're testing for an association between two categorical variables, the car's position and whether it comes to a complete stop. Normally when we test for an association between two categorical variables, we consider using a two-proportion z-test or the two proportions applet. But in this case, the variable car position has three categories, so we can't use a two-proportion z-test. There are three potential ways we could phrase our null hypothesis here. One way would be the same as we've done for two-proportion z-tests and two-sample t-tests, to say there is no association between a car's position and whether it comes to a complete stop. A similar version of this would be to say that the variables position and complete stop are independent. So independent is another way of saying that the variables are not related or not associated. In symbols, we could write the null hypothesis as pi sub single equals pi sub lead equals pi sub follow, where pi is the long-run probability that a vehicle of that type will stop. So our null hypothesis is comparing three different proportions rather than comparing two proportions like we did in a two-proportion z-test. The alternative hypothesis is that there is an association between a car's position and whether it comes to a complete stop, or that at least one of the three probabilities of stopping is different from the others. Notice that the alternative hypothesis is not that all three of the probabilities of stopping are different from each other, just that they're not all equal to each other. To test these hypotheses, we know that we want the p-value to be the probability of getting a result at least as extreme as what we observed in the data, assuming that the null hypothesis is true. But what result did we observe in the data? We somehow want to summarize the data shown in the table here into a single number that summarizes how strong the evidence against the null hypothesis is. We call this the test statistic. Previously, we've used test statistics of p hat, x bar, or the difference of two sample proportions, or the difference of two sample means as our test statistic. But when we have a table with more than two columns, it's not as clear how we can summarize the information in the table into a single number. To find the test statistic, we need to start by finding the expected counts. In other words, if the null hypothesis were true, what counts would we expect in each cell of the table? To do this, we start by finding the row and column totals. In other words, just add up the numbers across each row and each column. A good check of your arithmetic here is to make sure that when you add up the numbers in the total column on the right and in the total row on the bottom, you get the same total sample size, in this case 316. Now we can say that the overall probability that a car is a single vehicle is the number of single vehicles in the data divided by the total sample size. So 176 divided by 316. Similarly, the probability that a car comes to a complete stop is the number of cars that came to a complete stop divided by the sample size. So 265 divided by 316. Then we're going to use the multiplication rule for independent events to say that if the events being a single vehicle and coming to a complete stop are independent, then the probability that a car is both a single vehicle and comes to a complete stop should be the product of those probabilities. Then the expected count is just the expected value of the count from a binomial distribution, the sample size n times the probability p. So we have our sample size of 316 times the combined probability of being a single vehicle and coming to a complete stop. We can cancel out one of the copies of 316 from the denominator to get 176 times 265 divided by 316. So in other words, the expected number of cars in that upper left-hand corner of the table of the number of single vehicles that came to a complete stop is the sum of that column times the sum of that row, all divided by the total sample size. When we repeat this process for all 6 cells in the table, we get the expected counts shown in the second table here. Notice that because these are expectations, sort of like means, it is okay for them to have decimals, so we don't round these off to whole numbers. Now we're ready to think about the test statistic, a single number to summarize how strong the evidence in the observed count table is against the null hypothesis. So a way to think about this is how different is the observed data from what we expect if the null hypothesis is true. The statistic we use here is known as the chi-squared test statistic. Its formula is given on the right-hand side of the equal sign in the equation shown here. This looks complicated, but we can break it down. Observed sub I is the observed count in the ith cell of the table. So I would start at 1 for the first cell of the table and go up to 6 for the 6th cell in the table. Similarly, expected sub I is the expected count in the ith cell of the table. So for each cell I, we take its observed count minus its expected count and square it, and then divide by its expected count. Finally, the capital sigma tells us that we are adding up across all the cells in the table. Take a moment to think about what the smallest the chi-squared test statistic could be. The answer is 0. When the observed count exactly matches the expected count, then the chi-squared test statistic could equal 0. But because the numerator is squared, it always ends up being a non-negative number. So the chi-squared test statistic can't be less than 0. Now think about how you would fill in the blank in this sentence. The blank, the value of the chi-squared test statistic, the stronger the evidence against the null hypothesis. The answer is larger. The stronger the evidence against the null hypothesis means the more different the observed counts are compared to what we would expect if the null hypothesis were true. And that should give us a test statistic that is far from 0, that's very large. This means that in the multiple proportions applet, we're not going to be looking at values of the statistic beyond the value we observed in the data, only values that are greater than or equal to what we observed in the data.
The data here are in example 8.1, the stop data. So I'm going to press Control A to highlight all and Control C to copy. And then I'll switch over to the multiple proportions applet. I'll clear out the old data, the default data, and press Control V to paste in my new data. And then I'll click Use Data. So now the bar graph here is showing the conditional bar graph of the percentage of cars that stop, yes, given which position that they're in, single, lead, or follow. And from this, based on the differences in the heights of the bars, it looks like there may be some difference in the probability of stopping. Maybe following cars are slightly less likely to come to a complete stop. So whether or not there's enough evidence to reject the null hypothesis here is going to depend on our sample size. If I scroll down, I can change the statistic to the chi-squared statistic. And that tells us that our chi-squared test statistic for the observed data that we actually got is 4.728. Next, I'll click Show Shuffle Options. And if we shuffle this just once, what's happening here is the positions and the stop status are getting shuffled up. So we still have the same number of cars of each type, single, lead, and follow, and the same number of cars that either stopped or didn't. But we're mixing up which value in the position column goes with which value in the stop column. So we could also think of this as a bar graph where we're mixing up which column each car is in and which part of the bar, yes or no, it's in. And that will tend to create bars that are more equal in heights than what we observed in the data. So in this case, we got a chi-squared test statistic from our shuffled data of 1.259, and that's graphed in blue here. If we do this 999 more times, we end up with the distribution of our chi-squared test statistic. And notice that unlike the test statistics we've seen for other types of hypotheses, this is not approximately normally distributed. Instead, it's right skewed. It has what's called a chi-squared distribution. And that makes sense because there's a hard lower boundary that the chi-squared test statistic can't be negative, but there's no particular upper boundary that it's going to have. So now, to find the p-value, we want to count the samples that are at least as extreme as 4.728. And for a chi-squared test statistic, we're always going to choose greater than or equal to, because these are the simulations that gave more of a difference between the observed data and what we would expect under the null hypothesis. That's giving us a p-value of 0.092.
If we're using a 0.05 significance level, our conclusion here could be at the alpha equals 0.05 level, there is not enough evidence to claim that a car's position is associated with whether it comes to a complete stop. Or we could say there is not enough evidence to claim that any position of car has a different probability of stopping. Or we could say we retain the hypothesis that the variables position and complete stop could be independent. Remember that we never claim the null hypothesis, we only retain it because it could also be that the variables are not independent, that they're associated, and we just didn't have a big enough sample size to detect that. Another thing to note here is that our p-value was between 0.05 and 0.10. that means that if we changed the significance level to 0.10, then we would change our conclusion to reject the null hypothesis.